All right, hi guys, this is Mr. Gilmore. This lesson I'm going to try to get through. This is the 12.1 lesson, so the very first lesson of chapter 12. We're moving into something called a vector valued function. We'll talk about that in just a second. I like to call those VVFs, just for short, okay? Vectored value functions. Before we get in there, you're just going to look at my mug right for a second because I want to kind of paint a little picture for you guys before we dive into today's lesson. It will feel clunky just because I'm going to be moving between different cameras and then also showing different images on the desktop here. So I want to start with just our three space. So we're going back into our three space, right? So I've got my X and I've got my Y and I got my Z. Now imagine that I place a vector at the origin. So the initial point of our vector is at the origin, okay? And the terminal point of the origin. So I'm using this pencil as an example because the terminal point of our vector now becomes a drawing tool. Okay, so we're going to be using this vector as a drawing tool. So imagine that I place this vector, the initial point at the origin, and then my terminal point is the pencil tip, or it could be like a pen or a marker, whatever we're dealing with. And now I move that vector in space. Okay, as I move that vector in our space, what that pencil's doing, that tip, it's drawing, right? It's going to then sketch something into our space there, and it could be again a marker, pen, whatever we're using. It's going to sketch that into our space. Now, so if I were to then move this vector in a certain sense, I could actually trace out a part of a line. Okay, part of a line, or I could use this vector to determine a plane, right? As I rotate it around. Um, but imagine then that this vector not only can change direction, but it can also change magnitude. So it can then grow, right? It can grow in magnitude or shrink in its magnitude. And so if I were to like move this in direction and then at the same time shrink it, okay, what I'm doing is I'm tracing out what we call a space curve, which is actually one of our very first definitions we'll take a look at here in chapter 12. Now I'll have a better representation of this. I actually found an online tool for us to use. It's called a parametric curve grapher, and what it will do is it will actually plot in our space a a space curve. And so imagine again, this vector becomes a drawing tool, all right, to trace out basically a curve in space. So you can imagine all the uses of this, or maybe we want to map out a particle's movement through space, right, through our three space. And so maybe that particle's movement isn't linear. Maybe it has different aspects to it, different variables affecting its position. And so as our vector is moving, not only is it changing direction, but it also be changing in size, right? It could also be shrinking in size. And so we're looking at what we call a space vector and how we define then, or sorry, a space curve, how we define a space curve or how we represent it in our system is known as a vectored value function. Okay, so let's dive into our lesson notes here. I'm going to change the camera. So we take a look at this. I'm going to have to reset the camera settings and choose a resolution. There we go. It's going to be a little blurry. Okay. So we are looking at the 12.1 notes. I'll jump over to the textbook here in just a second. But if you have your book open, go ahead and turn to page 820, and you'll see at the very top we'll be talking about a space curve. So what we're defining a space curve to be is all the ordered triples such that each of the coordinates of this ordered triple, they're actually based on some function of t. And what we're really going to be seeing as we then carve out these space curves in our three space is that t really will, as we parametricize that in terms of t, it's going to be hardened to the fact that t really will represent time. As we see then, as we change our time in our space, where our vector then traces, where this space curve is then following. So each of our x, y, and z coordinates, as we see, are defined by an f of t, a g of t, and an h of t. So now we don't have necessarily these static and really could be any function. It's not just a static line or a static plane, but now we actually have this kind of variable impact of watching our particle xyz travel through our 3 space. Okay, so what we do then is we define something, right? We've got our space curve, and what we're going to actually then define is what we call a vector value function, or I'm going to call these VVFs. So whenever you see VVF come up, that just means vector value function. Now on page 820, there's a box, right, kind of the middle of the page, and we'll look at this in just a second, that defines this, and you'll see it in more detail. But here's how we define a vector value function. It's of the form, and we're going to be using lowercase r as kind of the default for vector value functions. So I've got the r vector, which is actually based on t. So notice that our vector is now a function, all right, thus the vectored value function. And what does this do for us? Well, our vectored value function in a plane says then our vector is then determined by an f of t and a g of t. So then depending on our value of t, it'll actually then plot where that terminal point of our vector is in our space. And of course, that's going to work not just in a plane curve there, but also in a space curve. We can also define it to be f of t, g of t, and h of t. Okay, so a vectored value function is actually a function that determines a vector, right? Now we can juxtapose this because what we are more familiar with are the scalar or real valued functions. So these are the RVFs. So RVFs are real value functions, or we can call them scalar functions. What does this look like as we juxtapose that in terms of a function based on our vectored value function? Well, if we compare them, here's what this looks like, right? A scalar example of a real valued function is anything that we can see with either a single variable or multiple variables. I just went with a multivariable example because we'll see this later on, where depending on my x and y values, that's going to determine a scalar, right? There's going to be simply a real value returned to me with the input of my x and y. But notice what the vector value, right, returns to me when I place when I choose some parameterized value for t. It actually returns to me a vector. And so this is just an example where we see each of our 3 f of t, g of t, and h of t functions. We can represent them as any form of a function represented with t as its input. So like for the first one, I've got this linear 3t plus 1. But for the second function, g of t, I've got this 2t cubed, so I've got this cubic. And then I have a cosine function, cosine of t, represented as our h of t. And so we can actually, and I'll show you this in a minute, we can actually use some of our technology to watch these vectored value functions kind of come to life. Because remember, it's that pencil, it's that drawing tool. So the vector's terminal point then becomes a drawing tool in our space. Now, so we're going to talk about, actually, I can talk about this domain thing first. Because we're talking about functions, right, whether they are real valued or vectored value, so these RVFs or VVFs, functions still have domain to them. They have domain. And so even when we've experienced the real valued functions with a domain, we're going to experience vectored value functions to have a domain as well. And so how is then the domain determined? Well, the domain of and you'll see there's my notation for my vectored value functions. The domain of a VVF, okay, a VVF of our vector R, okay, there's our vector value function R, is considered to be the intersection of the domains of the component functions f of t, g of t, and h of t, which means it still has a domain to it, and the domain is actually restricted by the intersection of each of the domains of the basically the components of our vector. So the component functions, the f of t, g of t, and h of t, whatever their domains are, they restrict then the domain of our vectored value function. There's a quick example here I just want to show you, and then we're going to jump over and look online at a tool I found. But here's a quick example of a vectored value function, r of t, where we have in our first, right, the f of t is a natural log of t, the g of t is a square root of 1 minus t, and then our h of t is just simply t. So if we think about our last function there, h of t, it's unrestricted. There's nothing that will affect the domain of that last one. However, we look at the first two, there is a restriction in the domain, right? For example, our natural log, the domain of t has to be greater than 0. And then if we look at our second function, the square root of 1 minus t, it also has a domain, right? It's limited up to a value of 1, right, including, which means I can plug any negative number in there, negative value of t. But because I have the restriction of the natural log of t and the restriction of the square root, it does narrow down our domain quite a bit. So the intersection then of those three functions would be simply 0 to 1, and that's not including 0 and including 1. That would be the only values that are then defined such that it would satisfy this vectored value function. So even though it's a vector value and each of those are individualized functions, the vector itself, the VVF, actually then has to adhere to the domain and restriction of the domain of each of the three, or even two if we're in a plane curve, of the functions, the component functions that it's built from, the f of t, the g of t, and the h of t. Okay, now here's what I'm going to do. I'm going to actually jump over to my browser here. So let me show you this. So I found this. So we're going to actually do a couple things with this. I'm going to show you first just the power of our vector becoming now a drawing tool. So with our vectored value function, remember with the VVFs, I can actually now draw curves in space. So now we know how to plot a circle, right? Our circle by definition, right? We have our rectangular coordinates of x squared plus y squared equals r squared. However, with this tool, this is called the parametric curve grapher, and which I have linked to the chapter 12 page, and I'll show you where that is in just a moment. But this parametric curve grapher, it basically shows this black, that you can kind of see it a little bit, but that black curve there, the black vector there, that is my now basically like tracing tool. That became like the pencil I was talking about, where my terminal point is the drawing tool, right? So what I can do is if I want to then trace out a circle in space, so you actually can if I were to, I can't change it right here. Basically, just imagine that I want to trace a circle in space. Well, I don't have to actually trace it with my rectangular coordinates, nor really with my polar coordinates. I can draw it with a vectored value function. So I've actually I have let my rectangular coordinates be my polar coordinates of cosine t and then sine of t. And this is actually just in the xy plane, so I've just let my z of t be 0. But I can animate this. So watch this. So as I animate this, we're going to watch the vector trace out our circles. The vector then becomes the drawing tool. See that? And it's actually tracing out where our circle is. So we actually kind of see where it's going to be tracing already. But imagine that we didn't see that blue circle at all. And as we then animate this, it's going to trace out what that circle actually looks like. So again, that terminal point becomes is like the marker in our space, and it's now plotting out where this path of our curve is going to follow. Now we can do this in other ways too. I can get a bit more creative here. Like what if I want to plot out, this is actually a rotated ellipse in our space. So there's a rotation of ellipse, okay? So it's no longer on either one of the restricted axes of xy, like xy plane or yz plane or xy plane or xz plane. It's actually rotated within our space. Now I can then trace this out with a vector. I can use a vectored value function to trace it out. If you take a look at my functions, I've got this half cosine t, twice sine t, and then I've got this sum going on, 2 times the cosine of t plus a half times the sine of t, and that's actually going to trace out this ellipse. So if I animate that, remember, so this is a neat part to watch this, because my vector is not only changing direction, but it's changing magnitude. Do you see that? No, it's changing direction and also changing magnitude, and it's tracing out that curve in our space. Okay, so this is a vector value function. This is what a vector value function actually does for us. It actually traces out curves. We can actually plot these curves in our space. Now, more specifically, now we just talked about the vector value function having domain as well. So let me show you what it would look like if I restrict the domain of a function. So this function right here is a simple one right now. It's just t cubed as my x, t squared as my y, and t squared as my z. So right now, if we consider this function, it's unrestricted, right? If I think about the intersection of my domain, all reals work for x, all reals work for y, all reals work for z. And so if I animate this, you can see that my t minimum is set to -5, my t maximum is set to 5. And so if I plot that, look at the magnitude of our vector changing. Now watch as it gets closer, right? It's changing direction, and it's changing magnitude, and it changes down to a 0 magnitude, and then it then evolves, it expands out to be a greater magnitude to trace out our curve. And that'll keep just animating, looping around as I let this play. So as I'm letting that play, right, you see again that we can trace out any curve in our space by representing it with a vectored value function. In fact, our lines, the lines that we experienced in our in chapter 11, those are really, we could represent our lines now not as just parametric equations or symmetric equations, but rather we can represent it as a vectored value function. Now, what if we restrict this function's domain? So let me actually restrict this function's domain and I'll redo this. So I'm going to change my z of t to not be t squared, but now I'm going to do 0.5. So now it's raised to the half. So in other words, now it's t square root. Now to really show this on the graph, I have to redraw the display. So let me redraw the display. And look what happened. Look what happened, right? It's now only half of itself because I've restricted the domain of 1. It restricts the domain of the whole vectored value function, right? Because now it's square root of t, so that means it can only then have t values greater than 0. So notice that it's not doing anything for our negative values of t, right? Because those don't actually satisfy my vector value function. But as soon as it hits 0, you'll begin to see there's our vector, and it's tracing out the domain of our vector value function. So that would be something as we look at restricting domain or looking at the domain of a function or determining the domain of a function. It is actually the intersection of the domains of each of the three h of t, g of t, f of t, g of t, and h of t, or in this case, like x of t, y of t, and z of t. So our x, y, and z are determined by some parametric uh, uh, value of t. And again, this is a good idea to actually consider t in more in terms of time, really, of time. Okay, so now let's jump back to actually in our textbook. Where are we? This is actually the 12.1 section. So we've looked at now this definition of our vectored value functions, both for a plane and a space. I wrote them in component form, but we can also write them in our standard unit form if we want to. Let's continue on. We're actually going to jump back and we'll talk about, let's actually look at another example of domain before we talk about, I think we do a sketch of the plane next. So let's go back to the lesson notes I have. Here they are. Okay, so in the lesson notes, this last example here that I have at the bottom of this first page is an example. So example one, this is actually something we would do in class together. So example one, it says to then find. So if we're given r of t is really then the sum of these two vectored value functions, capital F of t and capital G of t. Let's find the domain of this vectored value function r of t, and it's really based then on these two, here, let me cover my solution. These two functions. So f of t is the vectored value function cosine of t, negative sine of t, and then square root of t. And then my g of t is cosine of t, sine of t, and 0. Now remember, if we look at our second, if we look at so it's our r of t is restricted by any domain restriction, right? It's the restriction and it's the overlap, basically, right? The intersection of any domain restriction. Well, if I look at my g of t, and I consider my t values can go into cosine, consider my t values go into sine, and then I just have 0. Well, there's no restriction there, right? So g of t doesn't have any restrictions. But if we look at f of t, right, our capital F of t vector value function there, we have cosine of t, negative sine of t, and then square root of t. Well, there's no restriction for cosine of t and negative sine of t, but that square root of t, that's our restriction, right? We can't have any negative values of t. We have it to be 0 or greater. So then our solution then is, what is the domain of our vector value function here of r of t? Well, it's the intersection. So the domain of our function r of t becomes our basically the interval from 0 to infinity, including 0, and obviously then with the parentheses around our infinity. So that's our domain. You're going to do a couple questions on your assignment where you're going to determine the domain of a vector value function. And you notice that we're actually, there's kind of two lessons here, that a vector value function r of t can actually be represented as a sum of vector value functions. And there's several properties of vector value functions we'll see in our lesson notes. Okay, so I'm going to then, we're going to take a look as we move on within our notes here. There are ways to actually represent a either a rectangular curve in space by using a vectored value function, or really we can represent any object within space. So if we want to represent one of our like simple conics, such as like a hyperbola or a ellipse or you name it, circle, parabola, any sort of curve, even like a quadratic equation, or we can represent it in terms of our whatever curve we want to plot in space, we can actually represent it by a vector value function, or VVF. Okay, so what I can do here, this is actually an example you'll see in the text or in your problem set as well. It says represent the segment PQ by a vectored value function and by a set of parametric equations. So we'll see that we can actually turn this segment, which we know if we imagine a segment in space, we can actually represent it by using a vector to trace that segment for us. And we'll see this example come to life here in just a second because I'm going to use that parametric graph equation to show you this. So let me show you. Here's our here's our example where we're going to use point P and Q. Okay, so those are our endpoints of our segment, and we're going to be representing this as a vectored value function. Well, to do this, what I need first is to find a vector that's in the parallel direction of our segment. So it's easy. All I need to do is just determine a vector PQ. And so with my P and Q, I've determined the vector 2, -3, -7, right, as my vector PQ. What I also need to know then is put this into a vectored value function so I can represent it with and actually I do my set of parametric equations first. I kind of lied. I'll do my set of parametric equations first, and then I'll do my vector value function so you can kind of see how it comes to life. So my functions, right, or my parametric, as you see, I take my x, my y and my z, and I represent just like we did with our lines in our chapter 11. I've got my initial point, which I picked P, right, just any random point on my line, so I picked P, which you are going to want to pick P in this case. So pick P as your initial point, and then I've got my direction vector, which is my 2, -3, -7, and I determine my parametric. So I would get -3 plus 2t, right? That's my -3 x component, x value, x coordinate, I should say, and then my 2 as my direction component of my vector. And then y, the same thing, z, the same thing. I choose my y coordinate from point P, and then the y direction number from my direction vector PQ, and then do that for z. But notice that at the very end of my parametric, because I'm only tracing a segment here, I'm not tracing out an entire line, right? Just to trace a segment. I have my x, y, and z. I need to restrict the domain, okay, of that parametric. So it's really just going to go from 0 to 1. So notice that if I plug 0 in, I start at then my initial point P, right? All these will represent my initial point P, -3, -6, -1. But when I plug in 1, it represents my terminal point of my segment, or the other endpoint of my segment. It'll give me then that -1, -9, and then -8 when I plug 1 in. So again, this will only trace out just part of my line, right? Because I've restricted my domain of t, and also trace out all the points between 0 and 1. So it will actually trace out the segment. And so we can put this again in terms of a vectored value function very simply. We can just basically take our x, y, z that's been parameterized, and we place our function of x, function of y, and function of z into our vectored value function. So now r, this vector value function r, becomes -3 plus 2t, comma, -6 minus 3t, comma, -1 minus 7t, in the angle bracket there. So there is my vector value function. And again, I bring that domain restriction of t down because I'm going to restrict my domain of this because I don't want to trace out my entire line. I only want to trace out a part of my segment. So there's actually, I did this already. I put a graph of this in our parametric curve grapher. So I'm going to go back and take a look at that. I've got that here. So actually, let me open that up for us. Parametric curve of the line segment. Okay, so here's our line segment already plotted in space, right? So that's actually our initial point, that one that we can kind of see right there on our graph there where the vector is pointing. That's our initial point. And then as I animate this, you're going to see our vector not just change direction, but change magnitude to represent as it's tracing out this segment in space. So I'm going to go ahead and animate this, boop, and look at that. It's tracing it now. See, I've only restricted t from 0 to 1, right? 0 to 1. And that's what it's doing. It's tracing out that segment for us. So that's how I can actually represent that segment in our space by using vector value function, and of course restricting the domain of that vector value function to just represent the segment and only the segment. Of course, if I were to like change my domain, then I'd be representing something larger. Let's say, oh, I don't know, 5. Let's go to 5 and see what that looks like. So now we got just a longer segment in our space, right? It's going to take a little while to draw all the way down there. There's our segment in space from 0 to 5. So it changes where my initial point's the same, but it changes where my terminal point is. I'll go ahead and change that back to 1. Yeah, it's a little funky sometimes when you try to type in numbers. There we go. So there's our original segment. Okay, so that was our second example there by actually representing a figure, a curve. This is not really a curve, but a figure in space, and we can represent even the simplest things like a segment. We can also represent really complex things like curves. Okay, and I'll actually show you when we get to over to Canvas here in a second. The home page, I actually did this in. Actually did this not in this one, but in GeoGebra. I graphed some parametric curves. They're actually called knots, and I'll show you those when we get to Canvas. Okay, let's jump back to our then lesson notes here, and we'll finish this off real quick. So the next thing, what if we want to actually sketch a vectored value function and give the orientation? I'll explain what this orientation means here in just a second. So let's actually sketch a vector value function. Here is the vectored value function we're going to actually sketch here. We're just going to do a plane curve. So it's going to be our vector r of t, and then our plane curve, so our x of t and our y of t, or f of t, g of t, however you want to call them, is t cubed and t squared. So what I did was I actually, went back to my roots, and I picked I did a t chart. Okay, so I picked 5 values of my t. Okay, so I just started at -2. Didn't want to go too large because of that cube. So -2 up to +2, and just incremented by 1. Okay, so then I then found what is my vector then pointing at, right? So my initial, as you see my r being produced from my value of t. My r, I got -8, 4, -1, 1, 0, 0, 1, 1, 8, 4. And I remember this is my vector tracing this curve out, right? My vector is tracing this curve out. Let me actually, hold on, let me stop this real quick. So it stops doing that. There we go. So this is tracing the curve out. So then basically what I did was I just basically plot these as ordered pairs, right? I treat this kind of like an ordered pair because those are our x and y values. So now on my graph, so let me bring my graph up. Here's what my graph looks like. Okay, so I plotted each of those 5 points. I have my -8, 4, my -1, 1, my 0, 0, my +1, 1, and then my +8, +4 right there, right? So I got my graph, right, as I follow this. So imagine you can see that, and we'll see this in just a second. We see the vector tracing this out. Okay, there's a vector value function is tracing this out. Now to answer, so that's our first part, which is to sketch the vector value function. But then there's this other part that says give the orientation. Basically, what this means, orientation, is that if I want to watch how my function is changing as t increases, which direction then is what's the orientation of my vectors tracing. So when I say orientation, I mean um, as t increases, which way is basically the vector flowing, right? This vector value function flowing, and so that's why I have these little arrows on here. This is showing the orientation of this, because what it's going to do as t is increasing, it's going to trace down this way, and then it's going to trace up that way. Okay, so I'm actually seeing the orientation, and I've got this actually in the parametric curve grapher here. So I've got this already plotted for us, and I'm just looking at it from a 2 space. So there's is the what I did just from -2 to 2, right? So that's the what I graphed there. And so watch as I animate this, right? You get to see, yes, not only is it sketching out this graph, right? This parametric curve, but it's also, you get the orientation, right? As t is increasing, which direction sort of is the vector value function tracing. And so I put those little arrows in the direction that it's actually tracing. And so that's what you'll see also in the assignment. I'll have you guys sketch a vectored value function, and then give its orientation. And I think I'll have you do both a plane and a space curve. The space curve's a little trickier, but just do your best. We've been practicing trying to graph 3 dimensions. Okay. I also, before we do our next example, okay, I want to look at an example in the text book, and this is on page, let's see which one, page 822. So let's look at this. Oh, here's just examples of sketching a plane curve and sketching a space curve. So use those examples in the text to help you when you get to the assignment. All right, here's the one I want to look at, the very top example. What if we're given a function? We've recognized a standard function, y equals x squared plus 1, right? So we can actually picture that being graphed in our two-dimensional plane, right? What if we want to represent that as a vectored value function, right? A VVF. Well, what we can do is basically we want to parameterize this function. And so in some cases, it's really simple, just like this one. Just watch how simple the solution is. The solution then is just simply, oh, let's let x be our parameterized value of t. So this is right here. So just let x equal t, right? Because if x equals t, then in our vector value function, our basically that very first component of our vector value function will be just t, right? Because that's our x component. So just t, right, would be our function that's represented there. And then since we know x is equal to t, we basically substitute in t into our function there. So we have then t squared plus 1. Well, that's our y value. So now we have actually parameterized x and parameterized t, and we can then put those two. So if we let x equal t, that means y equals t squared plus 1. Put those into the um, put those into the vector value function of r, and we get our t as our first component, and then t squared plus 1 is our second component. And we could actually then put that into our parametric grapher if we want to, and it'll trace out this exact same thing. We'll see the vector again initially starting here at the origin, and it will point then as it traces along our t values, and it'll trace out that parabola. And again, we know the orientation because as t increases, we can follow where is it actually tracing, right? Which direction is actually tracing? That gives us the orientation. Okay, so I wanted to show you guys that because there are some examples where it's just dead simple. Basically just replace one of the variables with t, and you've got yourself a parametric equation that you can then use for both, right? But there are some examples now. I want to actually hop over and take a look at our lesson notes here. There's some examples that are not as simple as just replacing a value of t. You want to get a little bit more creative. So let's take a look then at example number 4 here at the bottom of our notes. So here's what we're going to do, okay? We're going to represent the plane curve again by a vectored value function, but our plane curve is now a bit more complicated. It's not just a linear where I can just simply replace one with the other, because what would happen is if I placed x with t, I still have to solve for y, so I get y in terms of t. But by doing that, by taking the square root, I get this plus or minus, which then just kind of breaks the function into a piecewise. And I don't want to break it into a piecewise, so I want to actually represent this with the value of t, and I want to get creative with this. So here's what, and you may recognize this. Here's what I saw. I saw the ability to actually square that x and square that y value such that I can cancel out that 16 and cancel out that 4. And then you also recognize that it also can fit into one of our Pythagorean identities. And so one of our Pythagorean identities that involves subtraction, there's actually 2 of them. But the one that involves subtraction, such that the the difference does equal 1, is with our secant function and with our tangent function. So here's what I got. I got a little creative here, and I let my x be, here I say that my x equal 4 secant t and my y equal 2 tangent of t. You see that? X equals 4 secant of t and y equals 2 tangent of t. And by replacing then x with 4 secant of t and y with 2 tangent of t, you'll notice that when I square this out, so here's what it looks like, right? When I square that out, my 4 squared becomes 16, which reduces my fraction of the first term. And then my x squared becomes my basically secant squared of t, and my y becomes then my 2 my y becomes 2 tangent of t. So then when I square the 2, it becomes 4. The 4 reduces, and then my y squared becomes just tangent square of t, which notice that it still holds my equation true. That was kind of my goal. I want to keep this equation true. And now I actually have this equation kind of parameterized in terms of t now. This is the equation of my function now in terms of t. And you'll see then what this does is why I chose these strategically is because now I have my x in terms of a t and my y in terms of a t. So I can actually graph this. I actually graph this and put this into my 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 parametric curve grapher. And so this becomes my solution, right? Where, oh, I did that wrong. I don't need my y equals there, right? I don't need that y equals there. I just put my 4 secant of t and then my 2 tangent of t. So I got my x function, my y function. So let's actually go ahead and let's jump over there and take a look at that graph. And that one I had to put, again, I'm sorry guys, this is a bit clunky. I had that one in my email. So real quick, I drafted that one. Here it is. Boop. Oh, yep, go there. Yeah. Oh, so one thing about the parametric curve grapher is that it doesn't recognize the function of secant nor tangent. So I had to actually put it into terms of cosine and sine. So I just converted it to cosine and sine. So there's my 4 divided by cosine t, which is my 4 secant t. And there's my y equals 2 times my tangent of t, which is my sine of t over cosine of t. And again, this is in a plane, so I just let my z of t equal 0. And if we recognize the original, like if we go back real quick and look at the original equation of our example, we should recognize what that conic is, right? That's just a hyperbola. Okay, it's just hyperbola. All right, and so which means I can trace out this hyperbola by using the vectored value function we determined, right? Again, I need to this needs to go away right there. It's just my 4 secant of t and my 2 tangent of t, right? That's my vector value function. So back to our parametric curve, we got this awkward lines kind of tracing through. Again, those are like kind of asymptotes, and the grapher doesn't know how to handle those, so it shows them. But we know that the hyperbola that we're seeing, that's where we're starting. So let me reset this. Okay, so there's our when our t is 0, and let's just watch this. I actually just going for a period of 2 pi. So the period 2 pi, because this is going to repeat itself. So when I go my period 2 pi and animate this, notice then, watch it, it's tracing out my hyperbola. And so there's a vector tracing out my hyperbola. It's going to go to the end of its limit there, all the way on the back, and then come back around and traces it all out. And then again, it resets itself because it just needs a period of 2 pi. And there we have it. We've actually can graph that curve in a plane, and I can actually change the orientation of this. So we're looking kind of straight down upon it. Let me spin this around. Whoa. Spin this around. There we go. So there's our graph, right, of our hyperbola, and it kind of actually we can kind of barely see our asymptotes in there. That's awesome, and that's our vector value function tracing out this hyperbola in terms of that t, right? That parameter is t, rather than the original function of the x squared over 16 minus the y squared over 4 equals 1. So there it is, right? That's what our graph looked like, and this is the power of a vectored value function of what we can actually do with vectored value functions. Okay, so your homework assignment, when you jump into it, the problem set, you're going to see examples like ones we've done here in our notes, but also you'll also do some investigations into other vectored value function information along the way. So I encourage you. Oh, one other thing, if you read through the rest of this lesson, there's a couple things we don't do, like limits and continuity. I don't have you guys determine the limit because basically you know how to determine limits. We will practice some limits later on with our vector value functions, but we don't actually need to do this now. You kind of see that it didn't render all the images, like the little arrows for my limits aren't there. Even down here, the little arrows aren't rendered properly. But everything that we've done, basically remember, because these are still functions, everything that we've learned with functions, the properties of functions, those all still apply with our vector value functions. And so we can see that we can take the limit of a vector value function in a plane and in space, and it basically is just whatever the limit of the vector value function is, it is then reciprocated to the individual component functions that determine that vector value function, the VVF. There's also continuity. Basically, right, if the limit exists, then it's continuous at that point. And so we can write we can determine continuity, which I don't have you doing any sort of examples like that in the lesson notes or in the problem set. You'll be jumping just right into the problem set, looking at domains. You'll do a matching game here. I actually have you guys do 19 through 22 there, a little matching. You work with sketching in the plane and the space, and then you also will work with taking these in this section down here. You'll be working with taking a plane curve and represent it by a vector value function, the VVFs. Okay, and so you'll take something like 47, where it's y equals x plus 5. You could replace x with t, so that's one of your x equals t, and then y becomes y equals t plus 5, and then you can transform that into a vector value function. If you recognize 53, that was the example we just did. Which is x squared over 16 minus y squared over 4 equals 1. That one we actually represented. We had to get a little creative with using our polar kind of features of x and y to actually help graph that in our plane. Okay, so that is all I have for you guys with 12.1. I know it was a lot longer, probably clunky because I'm going back and forth between notes and seeing me and the textbook, but hopefully that all kind of starts to solidify as you guys jump into the lesson and looking at the things you can do with vectored value functions that become quite handy as we want to trace out curves and stuff in space. If you do have any questions on this assignment or the lesson and something you're still not grasping, please email me. I'll get back to you with that. That's really all I've got. So be good and do good. Um, Actually, you know what? This is going to be awkward. I'm not going to stop it yet. I want to show you something on Canvas. Hold on. This is awkward. Okay. On Canvas, when you go to our home page, if you take a look at our multivariate homepage, that graph is actually just a space curve. Those are just knots. Actually, there's a name for those. Those are called space knots. And then if you go to the Chapter 12 course page, I do want to show you that I did link that parametric curve grapher here in the additional resources. So when you click on that, it'll just open up to the default parametric curve. They already have one set in there for you to kind of watch and see. But there's the there's the parametric curve grapher. I will warn you that Securely does block this at school. So hopefully by the time you guys watch this, they will have it unblocked so you guys can use it. Um, so yeah, I would recommend that if it's not working at school still, then wait till you get home and use a home computer. All you got to do is just basically Google or just come to Canvas and type, click on that link, or you just Google parametric curve grapher. It'll be like the one of the very first few hits you get there. Okay, don't use the GeoGebra one. It's kind of clunky. This one is much smoother. And if you are graphing a curve and it seems kind of like, I don't know, uh, too segmented, like it's too jointy, I guess, you can change the number of samples. And what that does is it increases the number of points it determines. And usually what I've determined is like 1,000 is a good one. So if I just type in 1,000, it moves a little slower just because it's determining more points. But it makes my curve a lot smoother. Okay. Okay. Sorry about that. I know I forgot that I was going to show you guys something on Canvas. So now that was a bit awkward ending. So now I'm actually going to end it here. That's really all I've got for you guys now. Email me if you got any questions. So be good, do good. I'll catch you guys when I get back to school. So let me go ahead and get that. Oh, get this stopped now.